Chips are making a huge impact on all our lives. Mobile phones, laptops, smartwatches, smart cars. Chips everywhere. So how are chips produced? Simply, it requires two stages: chip design and chip manufacturing. The design stage is to design the logical and physical structure of the chip, while the manufacturing stage is to create the actual usable chip according to the design plans. We will introduce the technologies used in the chip design stage. Chips are like digital brains. All data in the chip is represented in binary form. The numbers 1 and 0 are represented by the on and off states of the circuit. All the operations performed in the chip are realized by a structure called logic gates. There are many types of logic gates. For example, the AND gate has 2 inputs and 1 output. The output is 1 only if all inputs are 1, otherwise the output is 0. Like this circuit, the light is on only when both switches are on. When only one switch or neither is on, the light goes off. AND, or, NOT gate, are the most basic logic gates. The truth table can record the inputs and outputs of the logic gates. Different logic gates can be represented by the specific symbols. The logic gates that implement a subtask are packaged into separate modules for easy reuse, which are called macros. Wires are used to connect a large number of macros with different roles on a chip. How to place these macros in the suitable position to achieve the best chip performance is a key challenge in the chip design, also called placement problem. The placement problem is very difficult because the search space grows exponentially with range. The state space of Go game is about 361 powers of 3. However, the number of possible placement plans can be over 10 to the 2500th power. We cannot use a simple brute force method. How to score a placement plan? Experts score in 3 aspects: wire length, congestion, and overlap. The wire length is the total length of the wires. The following 2 plans, which one is better? The answer is the right one, namely, the shorter the wire length, the better, because there is a time delay in the propagation of signals on the wires. Shorter wires allow information to travel faster, thus increasing the speed of chips. Long wires can slow down the device. The second aspect is congestion, which is the crowding of the macros. The following 2 plans, which is better? The answer is the right one, because the macros cannot be placed too crowded. An overcrowded placement will lead to heat dissipation problems and block the information transmission. If congestion is not handled correctly, the device can heat up quickly. The last aspect is overlap. The following 2 plans, which one is better? The answer is still the right one, because the macros cannot overlap each other. It is a design rule based on chip manufacturing. If there is an overlap between macros, the chip will not meet the manufacturing requirements and cannot work properly. The placement problem is also an algorithm design problem. The inputs are macro sizes and connectivity relationships, and the output is the optimum placement solution. It has been studied for more than 60 years. We use advanced AI algorithms to find the best solution for the placement problem. Our first version method, mask place, which solved the visual representation problem of macros. It generates 3 feature matrices, including position, wire, and view to represent the placement state. The position matrix records all possible positions where the macro slides on the chip without causing overlaps. The wire matrix records the value of the increase in wire length that results from the added macro at each possible position. The view matrix shows the visual information of the current placement state. We input the 3 feature matrices into the placement model to find the solution. Mask place is an online method and has limitations. So, we propose our second method. Chip former. We collected existing placement data for pre-training. Also, we use a graph variant self-encoder to extract the connectivity structure features of the macros. State features and action features are extracted using similar methods as previously. Our method is trained on the transformer model to predict the next placement actions. In the results, chip former can learn from existing placement experience while further improving the effectiveness and speed. There are some examples of placement results based on our method. Chip former can reduce wire length by 60 to 90%, congestion by 50 to 80%, and maintains zero overlap between macros, while improving placement speed by 10 times. According to Moore's law, the number of gates on a chip doubles every 2 years. Therefore, there is still a big challenge to efficiently perform the placement of massively integrated chips. We will continue to improve our method to enable the chip placement with more macros. At the same time, 2D chips are gradually developing into 3D chips. How to effectively generate the placement of 3D chips is also one of directions we will explore, as we approaching the physical limits of the microscopic. Researchers are also looking for new ways to improve performance of the chip. The main directions include 3D chip stacking, new materials, neuromorphic computing, quantum computing, and optical computing. With the limits of Moore's law gradually approaching, the future of chip will involve a combination of these approaches, while relying on continuous optimization and innovation in hardware and software.